Have you ever looked up at the moon and asked yourself, how did that get there?
No.
Well, what we're going to do is show a simulation of how scientists think that might have happened. So we've got a planet called the early planet Earth on the right, and we've got a new planet called Theia, which is going to collide with the Earth. And this large explosion, this is much larger than an asteroid strike. This big explosion will throw enough stuff into the orbit around the Earth that in the years and decades following, the moon can form from that. This is just one simulation of how the moon formed, but the question that I want to answer in this video is what scientists think happened and how they know. Why do people think there was a collision, and how would that create the moon? Let's take a step back. Earth's moon is big. The only other moons of a similar size are around the gas giants, but the gas giants are so large that by comparison these moons look quite small. It's only really Pluto, which isn't a planet anymore, that has a similarly proportioned moon. So Earth's moon is at least a little bit unusual, being so large. So how did the Earth come to have such a large moon? To answer this, we can look at the stuff the moon is made from. Here is a graph of the oxygen 17 and oxygen 18 taken from various rocks. The blue dots are rocks taken from the Earth, black dots are rocks taken from the moon, and red dots are meteorites that we know came from Mars. To explain this chart, there are three types or isotopes of oxygen: oxygen 16, 17, and 18. All three of these are only made in stars and you can't make them in a planet. Most oxygen is oxygen 16, but about 0.2% is oxygen 18, which we're showing here on the y-axis, and a little bit less is oxygen 17, shown on the x-axis. If we look at the rocks from the Earth, they make a nice clean diagonal line, and this is because there are some processes, such as evaporation, condensation, or mineralization, that are still oxygen. This concentrates the oxygen 18, but it also concentrates the oxygen 17, and because it affects both 18 and 17, it just moves the rock up and down the diagonal line, and it doesn't shift them off this line. If we look at Mars, though, it's below Earth's line. It still makes a diagonal line, but it's noticeably different to Earth. Whereas if we look at the Moon, it is a good match to the Earth. When we look at other elements, the same story plays out, and this is a strong hint that the Moon is actually made of the same stuff as the Earth, and Mars is not. One way to explain this is that the Moon was just formed near the Earth, so it started off very similar anyway. Then maybe it just got captured by the Earth. But it turns out that's actually quite difficult to get that capturing mechanism working. This theory isn't particularly favoured at the moment because it seems like too much of a coincidence, and there are a few other points that doesn't explain that well either. Firstly, the Moon doesn't have a very big core, as you can see here. I've shown the inner circle here as the core, which is made of dense metal, dense iron, and the outer part is the mantle. The red part here is the mantle, which is made of much lighter rock, typically silicate-based rocks. Secondly, and not shown here, the Moon seems to have less stuff with a low boiling point, like zinc, than the Earth does. This all paints a picture of the Moon actually being made of Earth's mantle. It's not just that it's similar, it's actually that perhaps it was made from Earth's mantle. Something would have stripped a whole load of Earth's mantle out of the Earth, let zinc and whatever boil off, and then the rest would be put in the Moon. The only thing which we know about that could do this would be a huge collision. What astrophysicists have done is to try to recreate this in simulations. The idea is to keep trying different sizes of the two planets, different spin rates, different angles, different speeds, and you look to see if you can get results that match the real Earth and the Moon. What we're going to do here is show some similar, but admittedly probably less accurate simulations. I've tried to vaguely replicate the results from the literature, so we shouldn't be a million miles off. In these simulations we're running at about 450 times speed, which means that the body of the collision is probably about an hour long in real life. The way that these simulations work is that you take a planet and you pretend that it's made of thousands and thousands of particles, shown here by light points on the screen. Each of these particles represents about a billion tons of rock. When we follow the simulation through, this particular one ended up with far too little Moon. Most of the mass, which in real life would be vaporized rock, crashes back down to Earth, and there just isn't enough left in orbit to make up a full-sized Moon. If we throw the Moon at more of an angle, we can get more Moon. But the Moon and Earth are too different. They haven't been mixed nearly well enough. I've taken the Earth here in yellow, and I've coloured the particles making up the Moon in blue so that you can see how well they mix. I'm going to play one more video and let it run a little bit longer. It's worth stressing, though, that the point of these simulations is to see how plausible it is that a giant collision could form the Moon. You could always argue, though, that if you play around with the parameters enough, of course you'll be able to find something that matches experimental findings. But actually, the trick here is to see how difficult it is. So if you find that it's very easy to find parameters, then the theory is more likely to be correct. And if you find it's extremely difficult and the parameters need to be exactly right, then the theory is less likely to be correct. And what we find is that when we look at this, we find that it's fairly easy to make a moon. It's fairly easy to make even quite a large moon, but it's not that easy to get the planets to be well enough mixed. The way that people think this problem is solved, though, happens from looking carefully at what happens after the collision. Remember that these collisions are being played at 450 times speed, so they only cover a few hours. But calculations suggest that rock vapor would take a lot longer to cool down to form a solid planet, maybe decades, maybe even centuries. And this leads to a recent idea called a Synestia, which is a fast spinning planet with a vast atmosphere of rock vapor. And this atmosphere is actually so large, and the planet's spinning so fast that this kind of spills out into the space around the planet. So we've got here an image of a Synestia, which, although I rented this actually comes from somebody else's published simulation with credits at the end. You can see here a bright inner planet peeking through in bright red, and there's a huge cloud of dust and gas surrounding this. We're not going to show the spinning, but let's orbit around it to get a side view. Now we can take a cross-section through this, and we'll show the density in red. So you can see the much denser inner part of the planet still making a nice coherent blob in the middle, but this atmosphere now extends tens of thousands of kilometers into space. This atmosphere of rock vapor might well be the key to the mixing problem. Because the Synestia lasts for tens of years, this gives plenty of time for the two original planets to be extremely well mixed. It's only really as it starts to cool, many years later, that this starts fragmenting and separating into separate planets, and only then does the mixing stop. So is that the whole story? We've got the collision, we've got the isotopes showing that the Earth and Moon were properly mixed, and we've got the Synestia that explains the mixing. So there's just one more part of the puzzle. How does the Synestia form the Moon? I've got a fairly inaccurate simulation to try to illustrate this, but the truth is that this hasn't been perfectly modelled by anyone yet, because it's complicated and it takes a lot of computing power. There are also a lot of different processes here, from rock vapor condensing to potentially even magnetic force and magnetic fields to get this right. But basically, if we model the cooling Synestia again with lots of particles, you can see that at the outside of this spinning disk, further from the Earth, these particles start clumping together. The inner part might still be being mixed like ice cream, but over time, the larger and larger clumps of the Moon start forming at the outside. It will take a very long time for the simulation to complete with one Moon orbiting the Earth, but the key thing here is that mass is being more and more concentrated as time goes on. Before we end here, this is my first video, and I'd like to continue making more like this, with a combination of explanations and simulations. But what would help most is if you enjoy the video, it would be great if you could hit the subscribe button below.